Here is the question. It's test the convergence or divergence of the following series. This one here, just by looking at negative 1 the power n, gives me a clue that this is an alternating series. If we have alternating series, we should be able to use AST, alternating series test. For applying alternating series test, we have two conditions. In our series, except the negative 1 power n, the remaining part I'm going to name as Bn, which is this, which is clearly positive for all n. Our first condition is that limit n approaches to infinity of Bn should be 0. So let's check that. Limit n approaches to infinity of this is what we need to test. To find this limit, what I suggest is you find the highest power of n in the denominator. That is n cubed the power half. So basically that is n power 3 by 2. You can divide all the terms by n power 3 by 2. So in the denominator also you're dividing by that. But when this can go inside, it can look like n cube because it's a square root. N cube inside the square root is n 3 by 2. Okay, let's simplify that. Limit n approaches to infinity, n by n power 3 by 2 should be 1 by n power half square root 1 plus 4 by n cube. Now if n is approaching to infinity, 1 by square root of n will also approach to 0 and 4 by n cube will approach to 0. So what do we have? This as 0 divided by square root of 1 plus 0, that is basically 0. So our first condition of AST is verified. The second condition to check is that Bn plus 1 is less than Bn for most n, most values of n. Okay, so basically we want to prove that Bn is mostly decreasing. Mostly here means that if one or two or few finite terms in the starting are not decreasing, we can ignore that, right? So most sufficient large values of n, Bn is decreasing. To prove the decreasing part, I will write Bn as f of x. So f of x so this has to be written in f of x form. This will look like this. I'll find the derivative of this, and if I can prove the derivative is negative most of x values, then we should be good. So negative derivative means this is decreasing. How do you find the derivative of this? This is quotient. So I'm going to apply quotient rule. Square of the denominator is going to give me this times the derivative of numerator is 1 times square root of x cubed plus 4 minus x times the derivative of square root times 3x square. We can make common denominator by writing 1 here. When we make the common denominator, that can just come with denominator here. When we make common denominator, this is 1, so this number will have to be multiplied with this. So we'll have 2x cubed plus 4 minus this has to multiply with this, that is 3x cubed. That is going to be 2x cubed plus 8 minus 3x cubed divided by 2x cubed plus 4 power 3 by 2. So we have the like terms. 2x cubed minus 3x cubed is negative x cubed. So negative x cubed plus 8 divided by 2 times x cube plus 4 power 3 by 2. This is the derivative of f. Now, we want this to be negative, right? So we want basically this number to be negative. So x cube plus 8 should be negative. That means x cube should be more than 8. Okay. Why are we saying that? The denominator is always already positive, right? Because our x values are basically n values which are going 1 onwards, so that is already positive. And x cube for, it's x cube for 1 cube is not more than 8, for 2 is not more than 8. But if x is more than 3 or else, then x cube will be more than 8, right? So if you are more than 3 or equal to 3, then x cube will be more than 8. So we can say that f prime is negative for x more than or equal to 3, or we can also write it as strictly more than 2. So just for two terms like 1 and 2, this is not decreasing, but we can claim that using this part, we can claim that Bn is decreasing for sufficiently large values of n. Basically, we are saying for most values of n. So we have both the conditions of AST done. Number 1 is done and number 2 is also done. So we can claim using alternating series test, the given series, what was the given series? N from 1 to infinity, negative 1 power n divided by n cube plus 4 is convergent.